n1 is 1 plus nh, and dn dt is always n. So dn dt at t equals 1 means it's n1 times h, and n1 is 1 plus nh, so 1 plus nh times h. Yeah, does this make sense?
So anywhere where you say it's n times h, it's just n of whatever time step
Correct.
times h.
Correct. So in the general case, you can write n of, say, t is n of t minus 1 plus n of t minus 1 times h. So you can write 1 plus h n t minus 1. So here as well. So yeah, I should have h there as well. Oh no, that's not good. This is 1. So this should be 1. This is 1. So this is n of 1 is, n of 0 is 1. So this is 1. So this is 1 plus h. So this should be 1 plus 2h plus h square. So n0 is 1, and dn dt at t equals 0. dn dt at t equals 0 is n of 0, which is 1. You didn't follow at the back? Do you follow what's happening? If you don't follow, just let me know. Pass around this shine up seat. Like just write your name on this and pass around. So you write your name on this piece of paper. So you get plus h whole square. Now if I do the third step, and 3, then I get n2 plus n2 times h, which is plus h whole square plus h. Okay. Now this I can write 1 plus h whole square, 1 plus h, is 1 plus h cubed. Have you seen this before? This kind of numerical solution? Any of you? So did you follow this algebra here? How I got 1 plus h cubed? So you can see that in the general n of, say, time t, I'm going to get 1 plus h to the power t. Not t, yeah, it is. Should. Let's do a step small n. 1 plus h to the power n. And if you remember, if I take the limit of h going to 0 and n going to infinity, do you know what this tends to if you take the limit? It's this 2 to the power t, which also you can say from the exact solution. But if you take this limit, h going to 0 and n going to infinity, you will see exponential t. Okay? So that means your numerical solution also, in the limiting sense, is going to give you the result of the analytical solution. The only thing is, on a computer, you cannot make h going to 0. You have to have some cutoff. Okay? So, and that's the source of error in numerical solution. So that's another disadvantage of numerical solution. So you are getting a solution which is close to the real solution, but depending on h, you always get some error in your solution. Yes, you have a question? So let me see. So there are two kinds of errors in the system. One is truncation error. And that is arising because the Euler scheme, which I described here, okay, I don't know whether I wrote this explicitly or not. This way of solving first order or higher order differential equation using only the first derivative is called Euler scheme, okay, and it's widely used. And I'm going to show you that how you can use the same thing for higher order differential equation or a system of coupled equation. Okay, the same scheme you can use there. So, and this is arising because you are writing ft as f0 plus df dt times h plus half d2f dt2 h square, and you're ignoring h square and higher order. So you're ignoring quadratic and higher orders. Okay. Now tell me, if I increase the step size h, suppose I increase h, then what happens to this truncation error? It increases. Very good. Because if, as I told you, if h is suppose 10 to the power minus 1, h squared is 10 to the power minus 2. So the difference is not that much. So if you choose a time step of 0.1 and you do Euler scheme, you are already making an error of the order of 0.01, which may not be small in situations. Whereas if I choose 10 to the power minus 4, h square is 10 to the power minus 8. Now you see that h square is really, really tiny compared to h. Okay? So that's a much better approximation. Euler scheme is a much better approximation if you use a very small time step. Okay? So this error, the truncation error, that's going to go up, the truncation error. And then there is a second set of error, error 2, is round off errors. That arises because choosing up to a fixed decimal point. So you know what this means? Yes? What is this? So in each step of your calculation, when you're doing a calculation on a computer, you need to specify, okay, I'm going to keep up to second or third decimal point in my calculation. Okay? And when you do that, you are, suppose you are making some calculation and you get 0.123. And you are saying that I want to keep up to second two digits after the decimal point, so I ignore 3. Okay? So you are making a round of error there. Now, if your calculation involves fewer number of steps, so if you increase h, suppose you are solving some equation between time 1 and time 100, t0, t final. Okay? And now you choose h equals 1. How many times you are solving this equation? You are solving this equation for 100 steps. If I choose h 0.1, you are solving this for 1,000 times. Does it make sense? Now, if you solve this for 1,000 times, you are making such error 1,000 times. Okay? Whereas if you are solving for 100 times, you are making this error 100 times. So the round of error is going to be smaller in which case? When h is bigger. N is small. No, h is bigger, n is smaller, this case. Okay? So this error is going to go down like this, the round of error. So as I increase h, the round of error decreases and the truncation error keeps increasing. Okay? And this is like an optimal point where, so this step size h, you can say h optimal where you kind of optimized the truncation error and round of error. Because if you increase h, you are making large truncation error. But if you take too small h, you are ignoring round of error, not truncation error, but you have huge truncation error, huge round of error here. So small h, large round of error, small truncation, and large h, small round of large truncation. Or in between you have like a balance between those two. And okay, but there is one more thing to consider in this calculation, in this estimation of how to choose h. So the idea here is you decided to do Euler scheme, but how to decide h? That's a big question. How do you decide the time step? So in this equation, there are two things, major things, truncation error and round of error, choosing the time step h, but there is one more variable in this. What is that? What happens, like, this is all theoretical, but when you are doing it